So welcome everybody to another meeting of the Bohemian Cafe. And today we will have Jeremy Avigad. He's going to talk about methodology and metaphysics in Dedekind theory of ideals. And Jeremy, whenever you feel ready, the stage is yours. You can share your screen.
Let's see, let me share my screen. Okay, so if all has gone well, you're all looking at my slides? Yeah,
I can see them.
Very good. Okay. Okay, so so just by way of background, so this goes back to work that I did in the years 2003 to 2004, when I was supported by a New Directions Fellowship from the Andrew Mellon Foundation in New York. So the fellowship was designed to give researchers in the humanities cross-disciplinary training. And so I made the case that, as a logician and philosopher of mathematics, that I should have better skills in the history of mathematics. And so the fellowship gave me a year to study 19th century mathematics. And so during that year, I took classes at the University of Pittsburgh in history and philosophy of science. There was funding in the grant. I got to visit, I chose three excellent historians of mathematics. So Harold Edwards, John Stillwell, and Jeremy Gray. And they were, wonderful colleagues and consultants. And I learned a lot from them. But mostly, what I did was I read 19th century mathematics. I worked on my German, a little bit of French. I translated some of them. And looking back, I think that was possibly the most transformative year of my career. It really changed the way I think about mathematics, and it has had an influence on everything that I have said about mathematics since then. So as an outcome from the year, I wrote a long paper on with the same title as this talk. Looking back, I haven't really spoken about it much. I gave one talk on it in New York at an ASL meeting, but other than that, I think this is really the first talk I'm giving. So I do it with a little bit of trepidation. I mean, the work is already 17 years old, so I have to go back to the paper and try to remember what I knew or what I thought I knew back at the time. So I'm a little bit anxious that you'll ask me questions and I won't be able to answer. But it really is a good story, so I'm happy to share it with you. These slides are already online. The paper, of course, is online, and some of the old translations. And so yeah, let's get. Oh, and let me say also, please do feel free to interrupt with questions. I think, do I have? Yeah, I have the chat window open, but I might not notice it. So please feel free to just unmute and speak up. It'll be nice for me to know that that you guys are out there. Okay. So, oops. So most of the time when we do mathematics, it's just business as usual. We know when we sit down to can make conjectures, prove theorems, we know pretty much what the rules are. But throughout the history of mathematics, there have been times when mathematicians have had to pause to reflect on some fundamental questions about the proper way of proceeding. So I mean, even going back to ancient times, after Euclid, there's a history of discussion and debate over the nature of the axioms and the legitimacy of the axiom, the inferences in the elements. There's the 17th century, the shift from geometric foundations to more algebraic foundations, things like the use of infinitesimals in calculus. And of course, the whole 19th century transformation of mathematics and the shift to infinitary non-constructive methods. And even today, I think there are fundamental methodological questions about the proper use of computers in mathematics and so on. And so, when questions like this arise, there are, kind of different models as to how you should answer them, right? So one model is that, well, when you have a fundamental question, you should go to a quiet place and think long and hard about the nature and meaning of mathematics, the nature of mathematical objects and the way our language can possibly refer to them and so on. And you come up with some understanding of how mathematics works, and that should tell you, what's okay, whether it's, whether infinitesimals exist or not. There's the opposing view that philosophy has no place at all. It's all about mathematics, right? We're working mathematicians. Figure out what you need to get the job done, and and then just do it. So in his textbook on the philosophy of mathematics, Stuart Shapiro colorfully characterizes this as the philosophy last, if at all. And of course, what really goes on is somewhere between the two. So, when we do mathematics, we're all guided by some understanding of, what the rules are and what's allowable and what the goals are and what's acceptable. But, we're also working mathematicians, have a job to get done. And so there's kind of a balance between, just their day-to-day work and reflecting on their methods. And what I want to do is kind of explore the interplay between these two sides, these two views, in a certain development in 19th century algebraic number theory. Let me mention just in passing that some of the fundamental questions that arise can be posed or can be phrased as ontological questions. Questions about the existence of various mathematical objects. So, the introduction of zero, or the use of negative numbers, imaginary numbers, infinitesimals, points of infinity, kind of weird functions and monsters and counterexamples. Do they exist? And I think most of us feel today that questions like this don't have the same urgency, in the sense that now we do have a way of adjudicating them, right? We have informal or formal set theoretic understanding that tells us what sorts of things that exist. So if you want to talk about infinitesimals, well, you're working in a non-standard model, or you're doing or you're working some ultra product, right? You need some set theoretic construction that tells you what it is you're dealing with. And I think the set theoretic story does a remarkably good job. So I think that really does represent an important change in mathematics. But even today, I think there are still kind of ontological questions that arise. I mean, set theory gives us a very broad set of rules that tells us what we're allowed to talk about. But the question still remains what one ought to talk about. And right, so there's still a lot of thought that gets paid to that. Okay, so I'm going to tell you about the work of Richard Dedekind. So here's a quick biography. So he was born in 1831 in Braunschweig and really spent most of his life there. So he was a student of Gauss in Göttingen, not too far away. He received his doctorate in 1852. He then went to Berlin for a couple of years, and he was there. He was a contemporary of Riemann. And we'll see that later. He was very, very enamored of Riemann. He was very impressed, and held Riemann in very high esteem. But he, like Riemann, earned his habilitation in 1854. From there, he returned to Göttingen. He spent a few years in Zurich, but from there, came back to Braunschweig, and was there until he died in 1916.
Jeremy, I have a question.
Yeah.
What were the topics of the dissertation and the habilitation? Or at least the titles?
That's a good question. I don't know. So this is another one of those questions that I might have known in 2003.
Okay.
So look it up on Wikipedia, Steve, and then I'll ask you to report back to us by the end of the talk.
I'll look at Wikipedia and put them in the chat.
Yeah. Okay. Thank you. So, but Dedekind is considered one of the first modern, or one of the people who inaugurated modern mathematics. It's said that the great mathematician Emmy Noether, when people praised her work, she would very modestly say that es steht alles schon bei Dedekind, that it's all already in Dedekind. And of course, for Noether, that was incredible modesty. But there's a sense in which the quotation really captures a grain of truth, which is that so many of the things that we think of just being kind of hallmarks, emblematic of modern mathematics, one finds very clearly in Dedekind and not before him, right? So just a very comfortable use of infinitary set theoretic language, informal set theoretic language, the use of non-constructive arguments, the focus on algebraic structures and axiomatic characterization of structures, use of just mainstays of modern algebra. I mean, modules, fields, ideals. I mean, so ideals and lattices were his creation. focusing on, talking about structures, characterizing their properties in terms of mappings between them, the use of equivalence relations and forming new objects by quotienting by equivalence relations. We find that in lecture notes of Dedekind from the 1850s, in fact, in presentations of Galois theory. We'll talk about his emphasis on concepts and fundamental characteristics, and concomitant de-emphasis on calculation. And so, what my goal is today is to explore these features of his work and how they play out in the theory of ideals. So to motivate the theory of ideals, the prehistory actually, like a lot of things, goes back to Euler. So here's sort of one place where it crops up. Euler was trying to answer the question, so for what integers x is the quantity x squared plus 2 a perfect cube? And so Euler, interestingly, took the following approach to answering the question. So he factored, x squared plus 2 to x plus the square root of negative 2, times x minus the square root of negative 2, right? So he moved to the complex numbers, but he focused on complex numbers that can be written in that form. So a plus b times the square root of negative 2, where a and b are integers. So he gave an argument that these two factors themselves can't have any factors in common. And I don't remember the argument, but I was just thinking about it while preparing. And I think, the idea is you say if some quantity d, in the ring divides both of them, then it's going to divide their difference. So 2 times the square root of negative 2. And then I think you can argue then that so then d has to be a multiple of the square root of negative 2. So then you argue that d squared is going to divide this, and then you can use that to argue that x squared is x has to be even, but then you can argue that x can't be even for that to be a perfect cube, and so on. So whatever the details are, he argued that these two, if x squared plus 2 is a perfect cube, these two can have no factor in common. And then he argued that if x squared then is a perfect cube, right, because these have no factors in common, then they too must be perfect cubes. And to think about what's going on there, I mean, think about what happens in the integers, right? If two numbers, u and v, have no factor in common and they're a perfect cube, well, then when you take the prime factorization, every prime that occurs, has to occur to a multiple of 3, and it either, has to divide u or divide v, right? They have to divide up. Right? You can't split it across them, right? So if x squared plus 2, according to Euler, was a perfect cube, then so are each of these, right? So write x plus the square root of negative 2 as a perfect cube in the ring, right? And then you just expand, this is c cubed plus 3 c squared d, and so on, and set the whole parts and the coefficients of negative 2 equal. And then the numbers are really small. I mean, you can just, mess around. I think the only solutions are c and d have to be plus or minus 1, right? And you come to the conclusion that the only solutions to the original equation are when x is equal to plus or minus 5. And the conclusion is correct, and the argument is sort of correct, but there's an important gap in the argument that Euler either overlooked or just didn't bother to fill. Namely, that this argument, presupposes that, when you say that if x squared plus 2 is a perfect cube, then so are each of these, you're using this property that's true of the ordinary integers, but you're using unique factorization. And the point is that in general, unique factorization can fail in situations like this. So here's an example of where it fails. So if you consider instead numbers of the form a plus b times the square root of negative 5, right, then you can take the 6. You can write 6 as 2 times 3, but you can also write it as 1 plus the square root of negative 5 times 1 minus the square root of negative 5. Right. And in this ring, you can check, it's not hard to check that all of these are irreducible, so they can't be further factored. But this shows you that, unique factorization fails, right? And so, right. So, if this were the case with 5 replaced by 2, then, Euler's argument would have been faulty. And so it was, clear by the 19th century that, when you're studying properties of the integers, it's often useful to study number rings. So just finite extensions of the rationals and the integers in those extensions. And it was also understood that, or people began to understand that unique factorization, knowing when it holds and when it doesn't hold, I mean, that has some bearing on the situation. And so, Kummer's diagnosis of what's going on in situations like this is that, you want to restore unique factorization in some sense. And so what Kummer did was essentially he posited the existence of these ideal prime divisors, right? So in this case, the analysis is that, well, there are really these sort of magical, invisible objects, these ideal divisors, alpha, beta, and gamma. Once you can see them, you can recognize that 2 is. Oh, by the way, this twiddle thing is it's not equality on the nose. Whenever you're talking about divisibility, it's always up to associates. They're sort of each one divides the other. But the idea is that 2 is basically alpha squared, 3 is beta times gamma, and so on. So 6 is really alpha squared times beta times gamma, and these two factorizations just kind of divide up the factors in different ways. And the interesting thing is that, to talk about these ideal divisors, so what did Kummer do? The idea is, so first of all, the case that he was looking at is where the rings were, you start with the rationals or the integers, and you add a root of unity, so a complex root of 1. So, cube root of 1 or a fifth root of 1, or so on. Okay. But for, such rings, Kummer showed how to define predicates, P of x, which you could interpret as saying that x is divisible by the ideal, prime factor alpha. And there was no object alpha. I mean, these predicates were defined based on various data, right? But for each such predicate, you could think of there being this ideal prime alpha, such that, this thing described divisibility by alpha. So P of alpha, again, was defined just in terms of, ordinary operations in the ring of integers. And then he showed that, talking about these ideal primes alpha, obliquely through this property of divisibility, you could establish unique factorization, right? And so, according to him, it follows that calculation with complex numbers through the introduction of ideal prime factors becomes exactly the same as calculations with the integers and their actual integer prime factors. Okay. Okay. And I think, this is, so, it's already at this stage, it's useful to think about, so what legitimizes, talking about these ideal divisors as actual things. And more generally, the question of, why are we pushed to talk about, new abstract objects as things? So, there's a very nice report. So H.J.S. Smith was the president of the Royal Society, and on his retirement, he wrote a long report on the state of number theory at the time. And in the report, he wrote, the complex numbers of Gauss, Jacobi, and Kummer forced themselves upon our consideration, not because their properties are generalizations of the properties of ordinary integers, but because certain of the properties of integral numbers can only be explained by a reference to them. What I like to do is, focus on this language, that they force themselves upon our consideration, right? It's not like we make them up, or they're convenient, but they're there, and they're not only are they there, but they're kind of pushy. Like I have this image of, like the salesperson at your door banging on the door, asking to come in. They're really forcing themselves upon your consideration. Right. So in Kummer in 1846, with respect to the ideal divisors, he says, one sees that the ideal factors unlock the inner nature of the complex numbers, make them, as it were, transparent, and show their inner crystalline structure. Right. It's almost like he's doing chemistry, like he's understanding, it's like you're finding the atoms, the molecular structure, you're discovering things that are there. Okay. And so, I think when we talk about ontology and the philosophy of mathematics, what we need to explain is this kind of sense that some things, it's not like we create them, but they're there. They're there, and they've been there, and we're just discovering them. So anyhow, but here's a quick overview of the theory of divisors. So, from Kummer, so in 1871, Dedekind presented his first version of the theory of ideals. So he presented this. So Dedekind, as a student, sat in on Dirichlet's lectures on number theory. and he wrote them up and published them. So there's a publication that has come to be known as the Dirichlet-Dedekind or Dedekind-Dirichlet Lectures on Number Theory. They're Dedekind's write-up of Dirichlet's lectures. But then in subsequent editions, he started adding as appendices his own work. And so the first version of the theory of ideals was in as an appendix, one of the appendices to the second edition of the Dedekind-Dirichlet Lectures on Number Theory. Let's see, in 1877, there was another version of the theory of ideals he published in French as a separate pamphlet. But then again, so that was very similar to a version in 1879 that he published again in the next edition of the supplements to the Lectures on Number Theory. And between there was another presentation in 1878. Meanwhile, in 1882, we'll see, Chronicler presented his own theory of ideal divisors in a monumental work called Grundzüge einer arithmetischen Theorie der Algebraischen Größen. Let's see, in 1887, Dedekind came up with yet another version of the theory of ideals that he decided not to publish. In 1894, he published another version. Hurwitz published a version. There was a subsequent paper by Dedekind that a little bit obnoxiously, Dedekind said, of Hurwitz's version, that's basically the version I had in 1887, and I decided not to publish it because it wasn't worthy of being published. So it's a little bit mean-spirited. And then in 1897, Hilbert's monumental Zahlbericht, his report on the state of algebraic number theory. So there, I think, in the version I have, unique factorization appears on page 11, and it's Hilbert just it's very, very, very mature and sophisticated treatment. That's a quick overview. And so, you have all these versions to contend with, right? So you can look at, what changed between Dedekind and Kummer. And of course, the big thing is that, Dedekind generalized Kummer's theory from cyclotomic rings to, arbitrary rings of algebraic integers. He also determined the appropriate definition of an integer. And I'll come back to all of these things. But so there were technical questions about, there's special cases, having to do with the handling of primes that divide the discriminant. But probably the most important thing from our point of view is that he based the presentation on the set theoretic notion of an ideal. In 1877, and so in these two versions, which are very similar to one another, again, things had markedly changed from 1871. There's a cleaner algebraic separation. He's more careful to say, what things hold in modules, what things hold in orders, what things hold in rings. So he's, more the things are stated in more generality, more algebraic, care. Even though he uses set theoretic notions here, in some ways, in 1871, the presentation was a lot like Kummer's, that that the ideals were described in terms of calculational data. But by 1877, 1879, Dedekind has made a lot of progress in really hiding the calculations, and we'll see that was very important to him. Another difference, which I'll come back to, is that in 1871, the whole development of unique factorization is done in terms of greatest common divisors and prime divisors and so on, and only at the end you get the definition of multiplication. In the new presentation, he defines multiplication of ideals from the start, and that plays a central role in the proofs. One can also look at contrasts between Dedekind and Chronicler. So Dedekind uses set theoretic notions. Chronicler is much more explicit computational. So Dedekind used non-constructive definitions that Chronicler was very much opposed to. Dedekind avoids calculations of representations, which is the lifeblood of Chronicler's presentation. And throughout, Dedekind bases the presentation on greatest common divisors. But then, so again, 1887, there are further changes. So Dedekind gets the harder down to the proof to proving a basic property of ideals. So there's notion of divisibility for ideals, and he takes, the key property that needs to be established is isolated, and showing that if C is so if an ideal C is divisible by an ideal alpha, then there's some ideal beta such that C is equal to alpha. So A times B. So in other words, divisibility is defined not in terms of multiplication, but then Dedekind takes it. The key task is to show the that the definition is equivalent to the usual one in terms of existence of a multiplier. Okay. And then 1894, he just keeps pushing abstract. He keeps pushing to hide calculation. So again, I'll say, if there's anything at this stage I can clarify, feel free to interrupt. But I'm going to say more about almost all of these things.
Just to add something, it seems to me that recently Catherine Scale published a newly discovered version later than the last one you mentioned. I think it was published last year or even perhaps this year. I had no opportunity to look at the book, but I think that there was a new discovery recently.
Okay, interesting. So yeah, good. I don't know about that, but yeah, it'll be interesting to know. Yeah, what was there?
I have a question, Jeremy.
Yeah.
We all know what an ideal is in a ring, right? It's a subset closed under the additive operation and closed under multiplication by everything, maybe from one side or the other. That's a modern notion. That's what you mean when you say set theoretic definition of ideal. But a lot of us maybe don't know the other possible definitions. You say, oh, non-constructive or versus constructive, computational. What are we talking about here?
Yeah, so let me try to spell this out. So I'll invest a number of slides now in trying to spell out these differences. Okay, so yeah, so sit tight, and hopefully I will make that clearer. Okay, but another reason that it's interesting to study the history is that in addition to all these versions of ideal theory, Dedekind in his exposition often goes out of his way to explain why he's doing what he's doing, why he preferred one approach to another, or why he thinks that one way of doing things is better than another, right? So, if you gather all the data, so first of all, you have, all of these different Dedekind versions, right? So, 4 versions or 5 versions, maybe even 6 versions that keep changing. He's obsessively, he's just tinkering and changing and so on, right? So there's a lot to look at there, think at, what's changing and why. There's, contrast to Chronicler's theory and so on. So you can think about, differences there. And then on top of that, you have, Dedekind's all methodological pronouncements. If you're looking to do, a case study in, history and philosophy of mathematics, I can't think of one where there's just kind of more data than here. There's really a lot to look at and to work with. Right. And so when it comes to the methodological claims, when Dieterkind is explaining about what he's doing. So he says, again, the project was, as I read Dieterkind, I sort of made lists of all these methodological pronouncements and I tried to sort through them. And again, Steve, you'll get upset because I'm just going to run through these quickly. But again, over the next bunch of slides, I'll try to spell them out. But just to kind of foreshadow where we're going.
Since you've called me out, I get to answer. Can you just give us in one sentence? Just say it. What are we talking about? We have no idea what you're talking about. I know what an ideal is in modern terms, but what other possible definitions could there be?
Oh, okay, so it is the modern notion of an ideal, but Dedekind just refers to them as a system of things, right? And initially, they're systems of things satisfying certain predicates. He describes them in certain ways, but it's essentially the modern set theoretic notion before there was a language of set theory. So, back then when people talked about, so Dedekind, there's the word Gebiet. Sometimes he talks about domains of objects. There's System. So sometimes there's systems of objects. But it's, given a ring of integers, it's just a system of things, satisfying certain properties. So it really is the modern set theoretic definition.
Can I make a comment on that?
Sure.
You mentioned, I think, in one of the earlier slides that at some point that people were talking in terms of not the actual ideal as a thing, but as a predicate, the predicate of being divisible by this imaginary thing. And the ideal in the modern sense is, I would say, the extension of that predicate.
So that's exactly what it is. So that's exactly what it is. So Dedekind is taking the ideal object to be the set of things satisfying the predicate. And then the evolution is, how you over time, he then tinkers with the description of where the ideals come from, how you define these predicates. So there he kind of shifts away from Kummer. But again, the clearest way to describe the relationship to Kummer's is that instead of talking about the predicate of being divisible by alpha, you talk about the set of things that satisfy the predicate, and that becomes the object that stands for alpha.
May I make one comment too?
Sure.
I think what plays an important role is that many of the rings of the past were principal ideals. And so this means that the ideal is generated by one element. And so you can present the ideal just in terms of one element. And this is very related to Andres' observation of divisibility, I think, because everything boils down to divisibility by alpha at the end of the day.
Right. So unique factorization fails exactly in the case where there are non-principal ideals. And so the generalization of the theory goes from, the integers where every ideal is principal, to having situations where you have non-principal ideals, and these become the ideal divisors of Kummer.
And by the way, this is put forward by Dedekind, who is the one who introduces the term principal ideal.
I'm sorry, say it again.
I was just adding to what Ivan said, that Dedekind introduced the notion of principal ideal as opposed to other types of ideals.
Yeah. Yep. Okay. Okay. Good. So yeah. So in Dedekind's work, where he's explaining what he's doing, he continually emphasizes the importance of finding the fundamental and essential properties of the things you're working with, and often that's characterizing them in axiomatic terms. He constantly emphasizes that it's important that proofs should not depend on representations. Proofs should avoid calculations. There's an emphasis on generality. We'll see various types of emphases on uniformity and different kinds of uniformity. So being uniform within definitions, being uniform within proofs, and so on. There's an emphasis on for example, having unique factorization of ideals look as much as possible like unique factorization in the integers, and sort of developing the theory in such a way that it's analogous to more familiar situations. Right, and so that this will let you sort of reuse the proofs from the more familiar situations, but moreover, having the analogies will help guide the development of the theory. There's language that nouns should refer to objects. So when we talk about ideal divisors, there should be something that there should be a thing that they are. We'll talk about totalities of objects like ideals and real numbers should be defined uniformly and all at once. And they're also, language that points to methodological purity, that proofs should not depend on irrelevant features of the situation at hand. Okay, so let me try to spell out all of these. Okay. So for example, avoiding representations. So let omega be one of the non-trivial cube roots of 1, right? So if you look at the rationals together with omega, or the rationals together with the square root of -3, right? They're the same thing. As a field, they're the same field. Okay. But now when it comes to talking about the algebraic integers in the field, you might say, well, so maybe, maybe as Euler did, we want to think of things with the form, a plus b times the square root of -3. But if we think of it as generated by omega, maybe we want to look at, a plus b times omega, right? So there are two choices at what you might take the algebraic integers to be. And the answer is that the right answer is the first, right? There's a short argument that there isn't anything like a nice theory of unique divisibility for this ring, even adding ideal divisors. Okay. But then the problem becomes, well, so how do you know what is it? If you want to talk about the algebraic integers in this field, well, you want to do it in a way that doesn't depend on the representation. You want a definition that tells you that this is the right answer. And of course, the modern answer is to say that the integers in a finite field extension of the rationals, they're just the ones that are roots of monic polynomials, with integral coefficients. So, there is a modern definition, which is what Dieterkind used, that tells you what the integers are, right? But he makes clear that it's important to him that that definition tells you are what the integers are in any finite extension of the rationals that doesn't depend on the representation. And so in a similar way, Dedekind wanted to define the ideal divisors without making reference to particular, choices of representational data. Okay. So, here's a quote from Dedekind in 1878. So he says, "I first developed the new principles through which I reached a rigorous and exceptionalist theory of ideals 7 years ago. Excited by Kummer's great discovery, I had previously worked for a number of years on this subject, but although the research brought me very close to my goal, I could not decide to publish it because the theory obtained in this way principally suffers two imperfections. One is that the investigation of a domain of algebraic integers is initially based on the consideration of a definite number and the corresponding equation, which is treated as a congruence, and that the definition of ideal numbers, or rather of divisibility of ideal numbers, so obtained does not allow one to recognize the invariance that these concepts in fact have from the outset." So what this amounts to is that, in Kummer's theory, when Kummer defined his predicates P, P sub alpha, he sort of picked some representational data and he wrote down some expressions and he said, this is the predicate that defines the ideal. And Dieterkind is concerned that, it looks like, that definition depends on choices of representations. And this is not acceptable to him. He wants, definitions of ideals. It tells you what the ideals are, right? But without having to choose a particular set of representatives. Okay. The second imperfection of this kind of foundation is that sometimes peculiar exceptions arise which require special treatment. So he's referring to a kind of non-uniformity. So he says, my newer theory, in contrast, is based exclusively on concepts like that of field, integer, or ideal that can be defined without any particular representation of numbers. Hereby, the first defect falls away, and just so, the power of these extremely simple concepts shows itself in that in the proofs of the general laws of divisibility, no case distinction ever appears. Okay, so there's an emphasis on avoiding representations, on defining concepts, not in terms of representations, but in terms of somehow these essential features that they have, using algebraic characterizations and gaining uniformity and gaining generality. Okay. Right. And tied with this avoidance of representations is kind of an emphasis on concepts over calculation. So Dedekind is often contrasted with the Berlin school, such as Chronicler, Weierstrass, and so on, which favored a more syntactic computational style of mathematics. So in 1877, in this booklet that he wrote in French, in this presentation of the theory of ideals, he first starts by presenting, giving a presentation that's based on calculations to give some intuitions as to what's going on. And then he writes, but that even if there were such a theory based on calculation, it still would not be the highest degree of perfection, in my opinion. It's preferable, as in the modern theory of functions, to seek proofs based immediately on fundamental characteristics rather than on calculation, and indeed to construct the theory in such a way that it is able to predict the results of calculation. Right? So there's really striking claim that you don't want a theory based on calculation, right? It should be based on fundamental characterizations. And if you do it in the right way, then you have a theory that can tell you what the results of a calculation will be without making you do it. And so this is a striking quote, and we'll see more along these lines. A few years ago, I was interested to come across a quote by Galois from 1830. And I found it in actually a recent textbook by Tignol, who gives us sort of a historical presentation of Galois theory. But the quote goes, so if you now give me an equation that you have chosen at your pleasure, and if you want to know if it is or is not solvable by radicals, I could do more than to indicate to you the means of answering your question without wanting to give myself or anyone the task of doing it. In a word, the calculations are impracticable. Right? So he's presenting Galois theory and he's saying, look, I'm giving you a lot of calculations, but in practice, the calculations, they're just not practical. From that, it would seem that there is no fruit to derive from the solution that we propose. Indeed, it would be so if the question usually arose from this point of view. But most of the time in the applications of the algebraic analysis, one is led to equations of which one knows beforehand all the properties by means of which it will always be easy to answer the question by the rules we are going to explain. all that makes this theory beautiful and at the same time difficult is that one has always to indicate the course of analysis and to foresee its results without ever being able to perform the calculations. And so I've actually just requested this book from Interlibrary Loan to try to learn more about the context. So I don't know exactly what the context is, but what I find very striking is this idea that what we're trying to do is get a development of the theory that lets you, foresee the results, right, without being able to perform the calculations. Okay. And so we see that coming back in Dedekind. So here's another manifestation of the attitude. So Dedekind says, my efforts in number theory have been directed towards basing the work not on arbitrary representations or expressions, but on simple foundational concepts, and thereby, although the comparison may sound a bit grandiose, to achieve in number theory something analogous to what Riemann achieved in function theory. In which connection I cannot suppress the passing remark that Riemann's principles are not being adhered to in a significant way by most writers. For example, even in the newest work on elliptic functions, almost always they mar the purity of the theory by unnecessarily bringing in forms of representation, which should be results, not tools of the theory. So again, this emphasis on avoiding representations and basing not on arbitrary representations, but on foundational concepts. And just one more. In 1895, so even later, Dedekind quotes Gauss, a passage where Gauss says, in our opinion, truths of this kind should be drawn from the notions involved rather than from notations. So notions rather than notations. And Dedekind writes, when one takes them in the most general sense, a great scientific thought is expressed in these words, a decision in favor of the internal in contrast to the external. This contrast is repeated in almost every area of mathematics. One need only think of the theory of complex functions and Riemann's definition of functions through internal characteristic properties from which the external forms of representation necessarily arise. Okay. I'm trying to keep an eye on time, but I think we're doing okay. Okay, so let me try to to spell out a little bit more what's going on behind this. So I think it's useful to compare to the contrast between Chronicler and Dedekind regarding the construction of real numbers or the development of new real numbers. So for Chronicler, foundationally, we start with the natural numbers, right? So God gives us the natural numbers, and from there you construct the integers, you construct the rationals. Okay, and then if you want more numbers to calculate, so for example, you want to get a square root of 2, well, you pick a new symbol x, right? You can consider expressions ax plus b, where a and b are integers. But the idea is you baptize x to be a square root of 2 by declaring that x squared is equal to 2, right? And then you develop means of calculating with these expressions, using this to simplify. Okay, and there you've created the square root of 2. And so this way of proceeding it's based on representations and calculations. So if you want new numbers, you create symbolic representations and you explain how to work with them. Okay. And moreover, it's open-ended. I mean, you never pretend that you've constructed all the real numbers, right? As you need more things, you add more symbols, you give more rules, and you have to relate them to the old ones. But you're just constantly developing new representations and means of calculating. Okay. And of course, Dedekind's constructions of real numbers goes the opposite extreme. I mean, what you do is you identify the desired property of the structure of real numbers, right? What do you want the real numbers to do? And what you want them to do is you want them to fill the gaps in the rationals, right? I mean, the rationals are not complete, right? There's no square root of 2. You want to fill them up. So you identify the property, the design specification you're trying to meet. And then you build the reals to meet that specification, right? So Dedekind presented Dedekind cuts, right, and showed that they fit the bill, that they satisfy the principle of continuity. Okay, and then abstractly, you can think of real numbers as being Dedekind cuts, right? But once you have the algebraic the right algebraic structure, the real numbers are really sort of anything that's added. So you don't have to think of them as Dedekind cuts. They're just one particular model or one particular instantiation. And so, you get all the real numbers at once. And then, well, okay, then if you're worried about particular real numbers like the square root of 2 and ways of representing them and calculating and so on, you can go on and do that, right? But the important thing is to get the structural characterization. And so, in the presentation of the real numbers, he falls short. He doesn't identify the axiomatic characterization of categorical. But in 1888, he does a similar construction of the natural numbers and explicitly does establish categoricity. He says you give this abstract characterization, you show that there is something that meets the construction. You show that any two are unique up to isomorphism. And then explicitly, the natural numbers are anything, can be anything that satisfies the axiomatic description. Okay. And so, the approaches to algebraic number theory were similar, right? So, interestingly, Kummer, he, called these objects the ideal divisors. And so, when Chronicler went to develop the theory, right, he developed a theory of divisors, right? He had these symbolic expressions that represented the divisors, and he explained, how to represent them and how to calculate with them and, prove things on the basis of those representations. Whereas, Dedekind developed the theory of ideals. So it's funny, or it's at least interesting to me that, Chronicler, emphasized the divisor, the calculational, computational, and Dedekind gravitated towards the ideal aspect. Okay. So so let's come back now to this notion of the set theoretic notion of an ideal. And again, let me see how I'm doing on time. I guess I'm still okay. Right. So here's 1871. This is the first presentation of the theory of ideals. Okay. So Dieterkind is explaining why he found it advantageous to replace Kummer's predicates by his set theoretic, representations. So in 1871, Dedekind says that Kummer came up with a fortunate idea of feigning or creating such numbers mu prime. So these are the ideal divisors, and introducing them as ideal numbers. The divisibility of a number alpha prime by these ideal numbers mu prime depends entirely on whether alpha prime is a root of the congruence eta alpha prime congruent to 0 modulo mu, where here eta and mu are actual things. Okay. And consequently, these ideal numbers are only treated as moduli. So there are absolutely no problems with this manner of introducing them. So in other words, Kummer says what it means to be divisible by mu prime without saying what mu prime is. But whenever he talks about ideal numbers, he's only talking about their properties with respect to divisibility. So, it's okay to do that, right? You say what it means to be divisible by mu prime, and then you talk about divisibility by mu prime. But Dedekind goes on to say that the only misgiving is that the immediate transfer of the usual concepts of the actual numbers can initially easily evoke mistrust in the certainty of the proof. This has caused us to inquire after a means of clothing the theory in a different garb so that we always consider systems of actual numbers. So these are the set theoretic ideals. These are the ideals, right? These are the sets of things, the systems of things satisfying the predicates. Right. In 1877, he says we can indeed reach the proposed goal with all rigor. However, as we remarked in the introduction, the greatest circumspection is necessary to avoid being led to premature conclusions. So here he's talking about, again, he's talking about Kummer's computational approach of using predicates. He says, in particular, the notion of product of arbitrary factors, actual or ideal, cannot be exactly defined without going into minute detail. Because of these difficulties, it has seemed desirable to replace the ideal number of Kummer, which is never defined in its own right, but only as a divisor of actual numbers omega in the domain O, by a noun for something which actually exists. Okay. And as far as set theoretic characterization, let me just point out as an aside. So here's another striking set theoretic thing Dedekind does. So if you have a tuple of complex numbers, right, in 1894, Dedekind wants to define the number field, so the extension of Q generated by these complex numbers. And what he does is he does the modern thing. He says, well, take all fields, all subfields of the complex numbers containing alpha, right, and take their intersection. So it's the smallest subfield of the complex numbers containing alpha. But at the time, I mean, mathematically, this was just, as far as I can tell, this was really just out of nowhere. I mean, the Chronicarian, and I think the mathematically more natural thing to do is just say, well, they're just kind of quotients of polynomials involving alpha, right? You can say exactly what, what this field is, right? But Dedekind gives this very abstract and predicated, very heavy-handed definition. And you can ask why does Dedekind like this? But from his work, it's clear that it doesn't depend on representations. You don't have to say, well, choose polynomials and divide, right? You're sort of characterizing it abstractly in a way that avoids referring to the particular representations. It's a structural characterization. I mean, it tells you in particular that this thing is a subfield of any field containing the tuple alpha, right? And it's a very general method, right? You can take the intersection of things, it's just the general way of closing under taking the smallest thing, containing some elements. So again, it's very striking uses in Dedekind of set theoretic operations. Again, at a time where in mathematics, this really wasn't common. Okay.
Doesn't the second presentation require an equivalence relation as well?
Not if you think of these as the actual complex numbers.
Okay.
So no, I'm not saying taking them as symbols, but just take the actual complex numbers alpha and then just take the polynomials. So then they are complex numbers.
I see. But if you were actually using rational.
Yeah, if you were doing it kind of symbolically and quotienting, and so you would, and so what Chronicler would do is he would use an equivalence relation. But again, Dedekind would then take the set theoretic quotient. Okay, let me try to wrap up. I have a little bit, let me skip over just a few slides about familiarity. So let me just wrap up, and I can come back to say a little bit more about these during the questions, but I'd rather have more time in the questions and go back if necessary. So if you look at the recent philosophical literature on Dedekind, it's focused largely on Dedekind's metaphysical views. So for example, you look at the fact that that he was willing to talk about sets, infinite systems of objects, and he was willing to talk about operations on them. You can multiply ideals and so on. You can quantify over sets. You can do predicative constructions like the one I just showed. So I guess that that must make him a set theoretic Platonist, right? There's these infinitary abstract objects out there, and he refers to them and quantifies over them. So that seems like a kind of Platonism. But of course, Dedekind is the uber structuralist, right? I mean, so in terms of thinking about, algebra, characterizing mathematical structures and relationships between them, and and maps between them, and giving categorical characterizations of structures, and thinking of particular instances as just kind of abstracted from having a categorical description of the structure, right? So that makes him a structuralist, right? That mathematics is really about algebraic structures in some sense. But then again, in the construction of the natural numbers, there's talk of that being a logical construction. So people will also look at him and seeing kind of a proto-logicist. And I have nothing against this kind of philosophical pursuit. I mean, I think there's something to it. Dedekind is trying to work out this very broad global view of what mathematics is, and what the methods are, and what the basic objects are, and how they work. And so I think it's okay to look back on that and try to tell a coherent story about what the views were and how they all fit together. But I think that if you're trying to do that, it doesn't make sense to do that unless you think about mathematically where it's coming from. And so if the question is, what's the context in which Dedekind is doing all these things? Well, it's these, right? I mean, he's using these set theoretic constructions and these algebraic characterizations and so on, right? Because he wants to get at the fundamental essential properties of objects. He wants proofs that don't depend on representations. He's trying to avoid calculations. He's trying to do things very generally. He's trying to do things uniformly. He's trying to develop theories in analogy to other theories. He makes it clear, I think I skipped over the quotation where he's critical of Kummer. He says that when you deal with these predicates, but not having, without the set theoretic objects to stand for the ideals, that you're likely to run into trouble. You want to develop, your totalities of ideals and real numbers. You want general definitions that give you all of them at once, and you want your purity in your proofs. You want your proofs to really cut to the heart of the essential features of the mathematics and avoid irrelevant features. And so, and it's not that, you know, either one is prior, right? It's not that these are the things that Dedekind wants to do, and so he makes up this story that will let him do it. Nor is it the case that, you know, from the outset, these are the things he believes, and that just kind of guides the mathematics. But rather, there's this back and forth. I mean, he's got the mathematics that he wants to do, and he's trying to understand the right way to do it. And so, you know, kind of muddling along, you come up with these philosophical views while you're working through the mathematics. I mean, both of them evolved through the course of his career, and they evolved together. So, if anything, you know, my criticism, you know, of the philosophical literature is that it sometimes makes it seem as though there are two different Dedekinds, right? There's the mathematician Dedekind, who is, you know, trying to prove theorems, right? Trying to prove unique factorization of ideals, define ideals, and so on, and then prove unique factorization. And then there's the philosopher Dieterkind, who's making pronouncements on the nature of mathematics and structures and what kinds of things exist and so on. And, you know, we should keep in mind that there's only one Dedekind, and he's doing both of these at once. And it's not just Dedekind, right? So, you know, every working mathematician, well, you know, look, you've got to prove theorems, you've got to publish papers, right? So there's the task in front of you, right? But all of us harbor some understanding of not just what the rules of mathematics are, but what the goals are, and you know, what it means to do good mathematics. And so, you know, there's this constant back and forth between, you know, doing the task at hand, but thinking about what we're doing, and trying to do it well. And so, you know, if anything, the philosophy of mathematics can help us better understand, you know, think about this fundamental understanding we have and how it bears on the practice, and, you know, can help refine our views and you know, help us think about these things better. Right. And I hope I've convinced you that that, you know, to that end, history is a very powerful tool, right? So it's helpful towards understanding what it is that's important to us. So just looking at how mathematics, you know, evolved to be the way it is gives us a sense of what it achieves and what the goals are. So, you know, Lakatos had this view of, you know, the goal of doing history of science is to come up with a rational model of what it is that science is supposed to achieve, and then kind of use that to develop the history. So, you know, Lakatos wrote that in writing a historical case study, one should, I think, adopt the following procedure. One gives a rational reconstruction. You know, one, you give a rational reconstruction. Two, one tries to compare this rational reconstruction with actual history and to criticize both one's rational reconstruction for lack of historicity and the actual history for lack of rationality. Thus, any historical study must be preceded by a heuristic study. History of science without philosophy of science is blind. So the idea is you try to come up with a model of what philosophy of science is trying to, what science is trying to, sorry, you try to come up with a philosophical model of what it is that science is trying to achieve. And then you evaluate it against the history, right? And so, you know, the history should tell you whether you're getting the model right, and the model will help you understand the history. Okay, so in a subsequent paper, he opens with a, you know, a quote that's, you know, parallel to the Kantian dictum. The philosophy of science without history of science is empty. History of science without philosophy of science is blind. So you use philosophy of science to help your understanding of the history, and conversely, you use the history to help you understand, you know, understand science and its goals. And so, you know, if we're sloganeering, let me try one for the philosophy of mathematics. So I'd like to say that mathematical thought without philosophical reflection is empty. Philosophy of mathematics without mathematical content is blind, right? When we do mathematics and when we think about mathematics, right, we need to think in part, in addition to, you know, the everyday task in front of us, we should think broadly about what it is we're doing and why we're doing it, what the goals are. But to that end, you know, it's understanding, you know, the nature of mathematics and its goals. You know, you have to pay attention to the mathematical content, right? I mean, we need to keep in mind that philosophy of mathematics is the philosophy of mathematics. And so we should, you know, try very hard to listen to what the mathematics is trying to tell us and figure out what it's trying to say. Okay, so it's a good place to stop. So thank you very much.
Thank you very much, Jeremy, for this very nice talk. And now we move to question time. So if people want to ask questions, I see that there is already a couple of hands raised. So I would start from, oh, the hand disappeared now. I'm sorry. Okay, so I would say whoever would like to ask a question can unmute the microphone and just ask the question. Maybe Karine, let's start from Karine.
Thank you. Thanks a lot. Thanks a lot for this talk. It's always nice to hear that mathematicians are trying to have methodological ideas and think about them and do mathematics in accordance with them. I was interested in the value Dedekind gave to uniformity. So perhaps, I think it's important to say that even though we might be tempted to think of uniformity as a form of generality, he does not do so, but he distinguishes between the two. It echoes what you quoted from him in this passage from 1878 when you quoted a passage where he says that he wants to eliminate case distinction. And I wanted to ask you how you interpret this value given to uniformity. Why is it interesting to try to proceed in as uniform a way as possible?
Yeah. So, so that's a very good question. And so there, I don't have a really good answer, in part because I was kind of vague throughout the talk. And actually, while preparing the talk, I was thinking, oh, I hope somebody doesn't, nobody asks me about uniformity, because I don't remember what. So it comes up in lots of different ways in Dedekind, and I don't remember all of them. So in that particular quote, the way it's coming up, I'm trying to remember. So the issue was, and if there are any algebraic number theorists out there, they might know better than I do. But when you talk about the way, so when you go to these algebraic extensions, there's the question about how integer primes, primes, things that were prime in the integer, when they split, how they split, and so on. And in the development of the theory and in the definition of ideals, there are distinctions that if the prime divides the discriminant of the field, you do one thing, and if the prime doesn't, you do another thing. So in the definitions, there are two cases that get handled differently, and then in the proofs, if your prime is one, then you do this, and then otherwise you do that. And so in that particular passage, Dieterkind is pointing to the fact that the way Kummer did things, you had these case distinctions; they were important. But he has definitions and ways of doing things where, at least for some things, you don't have to make such distinctions. And so that particular quote was that particular example. He's saying that, my theory is better, it's nicer, we don't have to make these case distinctions. There's a very simple pragmatic answer that your proofs become shorter, right? It's, when you're reading a proof, mathematical proofs, if you open up a textbook, they try to be as very linear as possible. In fact, I'm writing an article on mathematical language for a handbook, and I sort of just opened up a textbook to think about, the OR elimination rule in logic, how you prove by cases and so on. If you just open up a textbook and look for proof cases, you really have to turn lots of pages until you find, mathematicians just naturally, proofs tend to be very, very linear. And so I think there is this very practical goal of, you want to eliminate case distinctions because the mathematics it's more efficient when it's linear. To have to sort of break a case, split into cases, then you have two different contexts, and then you go into one context and you solve it, and then you have to switch to the other context, and then things have changed. It's just inefficient. So there is this general methodological thing that uniformity. Avoiding uniformity, having uniform definitions just makes your proofs nicer and cleaner. But I guess there was also, in the talk, there was uniformity in the other sense. Dedekind has this uniform, what are the real numbers? They're just Dedekind cuts. They're not like the Kronikerian real numbers. Well, if you're talking about square roots, you do this. If you want to add transcendentals, you do that with different rules. So that was maybe a different sense of uniformity, of just having the whole domain of objects, all at once. And then among this big domain, then you can pick out representations of particular ones. And there, if the question is, what can be said of having a uniform definition, even if you care about computation, why is it important to have a uniform definition of the real numbers? I think that gives you an abstract touchstone against which you can develop your computational theory, right? If you know what the real numbers are, right? If you know what pi is, then you can talk about different representations of pi, and you can worry about whether something is equal to pi or not equal to pi, right? But you want to think of all these representations as representations of some canonical thing. And so having uniform descriptions of domains, that this gives you sort of this nice abstract setting where you know the objects you're dealing with. And then within that, your particular computational, you can have particular representations. So I think that's another answer, that uniformity is useful, that it gives you ways of tying together different perspectives on the same thing.
So thank you for the first question. I think now it's Andres.
Thank you. So I actually have a comment on something from very early in the talk when you mentioned that nowadays we have set theory to adjudicate ontological questions. I think that statement can have both a descriptive and a prescriptive meaning, and I'd like to mention something about the contrast. So the descriptive meaning is we have some ideas of what sorts of things should exist, the stuff we need to do mathematics, and marvelously, it can all be represented set theoretically, and we're very happy about that. The prescriptive view is sort of going in the other direction. If I can't represent it in set theory, I'm not so sure that that it even makes sense. I'm thinking of notions like the collection of feasible natural numbers, the ones you can count up to, or at the risk of offending any intuitionists here, the notion of a choice sequence, not just free choice sequences, but general choice sequences. What are those things? I haven't got a good set theoretic model of them. And there seems to be a general reaction, well, if you haven't got a good set theoretic model, you're not making a whole lot of sense, are you? And it's not obvious to me that those things really don't make sense. It may just be that we haven't understood them well enough to maybe well enough to figure out a set theoretic model, or maybe well enough to work with them in some other framework. So I realize I'm not sounding very much like a set theorist here, but I would like to see the possibility that there might be some good stuff out there that the set theoretic ontology misses.
Yeah, so I agree exactly. I agree entirely. So again, I think, mathematicians have this kind of funny attitude towards set theory. That, I mean, mathematicians have no idea what they can't tell you what the axioms of set theory are. And somehow it's comforting to know that they're out there, right? I think in part there is this feeling that, yeah, if your mathematics is rigorous, then you should be able to spell it out in principle and set theoretic terms. And if you can't, then there's something that is at least not sufficiently well understood, right? So you may have a heuristic. The theory might be interesting and may be doing useful things, but at least there's something that needs to be filled in. Yeah, well, I guess your comments weren't really a question, so it's okay that I don't really have an answer. but so I think that's right. I mean, I think so. I think one can think about objects in contemporary discourse where there seems to be fruitful mathematical discourse, and yet not an imperfect or fuzzy understanding of how one would or should express it in set theoretic terms. And so if that only highlights the fact that broad ontological questions are still around, are still pressing, I agree.
So there was one hand raised by Steve, but now it's not raised anymore. Steve, do you want to ask a question or not?
Well, I can ask a kind of vague question, and maybe Jeremy will be able to sharpen it up for me. The reason I put my hand back down is I couldn't sharpen it up myself. It's hard to understand what's even going on in this debate, as I already expressed earlier, because I just can't put myself into that setting. I guess I would have to know more about the mathematics of the day, and as a non-expert, I don't. So that's the problem. Like the problems, so the mathematical issue seems to be something like, how do we introduce possibly new elements into mathematics without knowing what the rules are for doing that? So that's maybe what's happening here for the first time. And we have to remember that they don't have, not only do they not have set theory, they don't have any kind of rigorous foundational system. They don't have the idea of foundations. They don't have the axiomatic method. They don't have the idea of writing down some axioms and looking at what the formal consequences are of those axioms. So the whole kind of point of view of modern mathematics is just missing. And so it's really hard to get yourself into that mindset where you want to have some new mathematical elements or something, but there's no systematic way of doing that. And so if you think about it from those terms, you might think, well, okay, I just write down what the rules are for these things in the sense of how do I calculate with them? Or I write down some names for these things, and then I say what their basic properties are, or what. And I guess maybe what Dedekind is contributing, or what we see developing through Dedekind's successive attempts, is this idea that we can somehow represent the new elements by collections of other elements or functions or something on the other elements, so that we build up the new elements, or we represent the proposed new elements using, I don't know, I mean, set theory, to say set theory sounds like we need ZFC. It's not that complicated. It's just taking collections of other elements to be new elements is already a radical idea.
Yeah.
So there's all this kind of conceptually new stuff happening, and then there's the accompanying question of, is that even legitimate? Is that mathematics? Are we allowed to do that? Who decides? That kind of stuff. So I don't know, I'm just kind of rambling on here, but
Yeah,
it's hard to get into that mindset.
Yeah, I think you're sort of rambling or kind of emoting in exactly the right direction. I mean, I think you can take this to be a story of where set theory comes from. I mean, what I don't like about it, a lot of the conventional tellings of the history is that, Cantor, woke up one morning and decided that there were infinites and so on. And then all of a sudden there's set theory, and then mathematics, said, oh, great, there are sets, and that just changed mathematics. In the 19th century, I mean, look, people have intuitions. And so, yeah, so in, the Chroniclerian vein, right, it's, when you introduce new objects, you just symbolic expressions, and there's kind of a manner of describing new constructions and explaining how to work with them. And again, they're relying on some intuitions as to how you can describe expressions and calculations and computation. I mean, Dieterkind is doing exactly the same thing with this incipient set theoretic terminology. I mean, there are lots of words that he uses. He uses systems, again, they're the words that he uses. There are the operations that we can look back and say, well, he's just taking an intersection of this, or right. And the question is, where does it come from? Well, again, the story I tried to tell, it's a mixture of, there was the mathematics he wants to do. He's trying to solve, very concrete, it goes back to, questions like, is, x, under what, for what values of x is x squared plus 2, a perfect cube, right? They're very concrete questions, right? So you've got concrete mathematical questions you're trying to solve, and you're developing methods to solve them. And in the background, you have some intuition as well. Okay, I can take this system of things, and I can take, I can do these operations. It's kind of a messy process. I mean, so one thing that's interesting to me is there are places where Dedekind goes on and on and on explaining why he's doing what he's doing and giving justification and why this is preferred and so on. And then there are places where Dedekind just does things without. So, for example, taking the fields, describing the fields generated by elements by taking the intersection of all of them, he just does it. He just says, and he just writes down the definition, and no hand wringing. What does this mean? What are infinite totality? He just does it, and so there has to be some intuition that says, yeah, that this is okay. So I guess the story I'm trying to tell you is that, when people like Dedekind start introducing these ways of talking about sets and systems of things and functions and so on, they're balancing, again, pragmatic mathematical goals with general intuitions. And over time, these intuitions get kind of spelled out and so on. I mean, this is where set theory comes from. Then people start, talking about, well, what does it mean to talk about a systems? And then you get, the informal mathematical language starts to settle and gel, and then then there are the set theoretic paradoxes, and then there are axiomatic systems. But that's kind of, so the axiomatic systems are kind of the end of the process, right? There's this kind of long, tortuous, just kind of messing around with the mathematics and trying to do the right thing. And axiomatic set theory is just kind of like it's like an endpoint. It's kind of a clarification. Here's a description of what we were trying to get to all along. Yeah, and I think it's really interesting for that reason. It's there isn't a clear articulation of the rules when Dedekind is working, so he's kind of making things up as he goes, but it's not anything goes. It's not like you can just make up anything. I mean, there has to be somehow some way of making it compelling, and I guess the way of making compelling is well, okay. So the question is, when you do these kind of ontological expansions, how do you make it compelling that it's reasonable, that it's safe? I mean, there are two issues. One is it useful, right? And it's useful if it gives you good mathematics. And the other one is it okay? Is it meaningful? Is it, is it just nonsense? Is it, is it meaningful? Will it lead you to errors? I think one way it happens is that you sort of get these quasi-conservative extensions. So Kummer initially had these predicates. The move from talking about predicates of things and just calling them sets, I mean, that's just terminology, right? So I think, the way it happens in mathematics is you do things that, they are some kind of expansion, but you can view them as just kind of convenient ways of rephrasing what went before. I mean, so for example, if you look at, an early algebra, if you look at the early algebraists, for example, the literature on, just solutions to the cubic, people just did not want to use negative numbers, right? So you have these different cases. There's the case where x cubed plus ax equals b and x cubed plus b equals ax, right? There was this avoidance of negatives because there's this geometric interpretation. You want these things to be lengths, and so negatives they're not lengths there. But then, okay, it's after doing all these cases, it becomes clear that if you just introduce negatives, well, most of the time you can reinterpret talk of negatives in terms of, you can interpret it away. So it's reasonably safe, but it's convenient. And then gradually you kind of accept them. So I think the way we get sucked into it is they're useful, and at least in the initial uses, they're just close to reformulations of what we were doing before. And then you get used to them and so on. And yeah, so if the question is, how did we get to modern set theoretic language? I don't think it's a simple story, but I think it's this process of trying to develop means that were useful for the task at hand, and then trying to convince ourselves that, that it's meaningful, it's safe, it makes sense. Yeah, and the only way to get at that story, I think, is to look at the history and try to make sense of it.
So we have a question by Marcus now.
Hi, Jeremy. Thanks for a very good, very informative talk. I just have a question about a slide that you had fairly late on, I think in connection with Dedekind structuralism, where you mentioned the case of the real numbers, where it says, he introduced the Dedekind cuts and showed that they satisfied Dedekind completeness, and the other, let's see.
Concepts, what I see. Yeah, this one Chronicler and then Dieterkind.
Yeah, Dedekind cuts has a desired property. And then the real numbers are anything meeting that criterion. Now, my question is, it really comes from ignorance together with a hazy impression. Did Dedekind actually say that the real numbers could be anything, that any system of things that meets the criterion?
Yeah.
Or did he say, well, I created the Dedekind cuts and they are the real numbers?
Yeah, so I worried about this a little bit while I was making up the slide. So my memory is, so in that work, he does not. With the natural numbers, he is absolutely, yes, he is very explicit. So the title of the essay is, was sind und was sollen die Zahlen? So what are the numbers, or what should they be? And the answer is very explicitly, it's anything that meets this categorical description. I believe with the real numbers, there's a letter to Kefferstein that you can find in the Ewald source book, for example, where he explains that he doesn't want, he doesn't think of these as being the real numbers. Rather, you have a system of things that has the desired properties,
right?
And then you sort of composite new objects that stand in correspondence to those. And the reason he wants to do that is that, if you identify the reals as Dedekind cuts, then the real numbers have properties that they shouldn't have, right?
Yeah.
That, like 2 is an element of the first component of 3. I mean, it just makes no sense for talking about the real numbers. It's just an artifact of the particular construction. So there is this, this modern, philosophers have attributed to Dedekind this notion of Dedekind abstraction, that you define a system of things that has the properties, but then you posit new things. You don't want to say the real numbers are the Dedekind cuts. You want to say that they're things that are in correspondence with them. And so in the essay on the natural numbers, that's explicit. And I believe, so it's not in the 1872 essay, Schwierigkeiten und die rationale Zahlen, but it is, I believe, pretty explicitly in the letter to Kefferstein.
Okay, so by the time he writes that letter, it seems as though he's now kind of developing the rules for introducing new things that Steve was talking about, because you still have to show that there is a system that meets that satisfies the criteria, or satisfies the rules or the axioms, and then you can say, well, anything else that satisfies them, they can also count as real numbers.
Right. Yeah. I mean, the recipe is very clear in 1888. You give sort of an axiomatic characterization of a structure. You show that there's at least one instance. You show that any 2 instances are isomorphic, and then you abstract, and then you get the new objects.
Yeah. Okay. Yeah. Thank you.
So we have more questions. Before I would like to make a comment, and then I will give the possibility of asking questions also to the other people. So at some point we discussed about uniformity and the importance of uniformity, and then I've been in queue. So I wanted to say it before, but then there was kind of queue. So and you advocated that uniformity is important. I will trivialize your answer, because we are lazy. And I think that's true. That's absolutely true. we want we want to work as little as possible, and so having uniform argument is convenient as a fact. But I think there is more than that, and by that I mean that as mathematicians we sometimes write down what we struggled for. So we worked on something and it was not easy to prove it, and we write it down. And sometimes when you work when you want to shape a phenomenon, two different phenomena, you have the impression that they are kind of similar, but you don't see why. And there is this intellectual tickle to understand why they are similar. And you start working to describe that, and it's not easy. And at some point you understand it. So you get to uniformity as a kind of intellectual tickle. And at that point, you fought for it. You had to struggle to understand it. So it cannot be irrelevant. And so you write it down because you think it's an achievement that you made in the process of understanding two different phenomena that you thought were different, but after all, they are not that different. So, and I think this is a little bit different from just conveniency of uniformity. It's also a kind of checkpoint of understanding sometimes.
Yeah. So let me respond in two ways. So first of all, I want to defend the value of laziness, and I want to give it a more positive label. So I prefer to think of it as cognitive efficiency. I mean, the remarkable thing about mathematics is that it's hard, right? And solving mathematical problems is hard. Mathematics has to do very hard, very complicated things, and a lot of the history of mathematics is learning how to extend our cognitive reach by doing things more efficiently, learning to find representations that suppress information, make other information salient when needed, and so on. So, I don't want to downplay laziness as a virtue. I think it's important for philosophy of mathematics to understand how it is that mathematical language and method makes it possible to think better. And so I want to push back a little bit on that attitude that that laziness or convenience is not. I think that's really a very important part of the story. But that said, I absolutely agree. So again, I felt a little bit guilty that I just kind of threw out the word uniformity because it's a good, colorful, useful word to use. I mean, I was kind of vague on what it meant, and uniformity in the talk was used in lots of different senses and so on. I mean, in your comments, I think you're thinking of uniformity as a partner with kind of generality. Like you've got two things, but in fact, there's actually one commonality that explains them both. And by finding that commonality, you're killing two birds with one stone. You're finding the one stone that can kill the two birds. And I think that is another important aspect of uniformity. Again, or generality or algebraic abstraction and so on. And again, it does a lot of things, which I think can also, many of them can be spelled out in terms of cognitive efficiency. You get concepts then in explaining both of them. They're more general. They manage information better. So in that sense, so I do agree. That is another important aspect of uniformity, of sort of finding the common features between similar things so that they actually become instances of some common thing.
Thank you for the answer. I didn't mean to insult laziness, which I respect a lot. So now we have another question from Andras.
Okay, thank you. So this is building on something that Stephen said several comments ago about the before set theory came along and people were writing down symbols for computations and so on, and developing rules to manipulate them and so on, without necessarily having what we would now consider a firm foundation for that. And I guess what I'd like to point out is that this is not just a 19th century phenomenon. It's a 20th and 21st century phenomenon, though not so much in mathematics. I mean, if you think about, for instance, the history of distributions, Dirac introduced the delta function and its derivative and all that other wonderful stuff back in the 1930s, I think, maybe even late 20s. A firm mathematical foundation was provided by Schwartz in, I think, 1954. In between, there were these rules for how you calculate with distributions, which the physicists happily used, and the mathematicians were shocked that anything ever came out of this stuff. And I think this is very similar to what Stephen was describing in the pre-foundational 19th century. And I think we're still in the same situation when it comes to quantum field theory. As far as I know, they have not yet proved that there is a non-trivial quantum field theory in 3 space dimensions plus 1 time dimension, which seems to be what we've got here. Nevertheless, those physicists are calculating, they got the magnetic moment of the electron to 9 decimal places, maybe more by now. And it works, and it works great. And we still don't actually know what they're talking about. So this seems to be a perennial problem, not just set theory came along and now we know everything. By the way, maybe I should, as long as I've got the floor, I'll mention a much shorter comment about Dedekind preferring the impredicative definition of the field generated by some numbers, rather than defining it more constructively in terms of rational functions of those numbers. I think part of the advantage of the impredicative definition is that it makes it obvious that that thing is a field. If you use the rational function version, you're back to computing. You have to show that the sum of 2 rational functions is a rational function. Yeah, we all know that, but it is a computation.
Yep. Yeah, no, I think that's exactly right. And that, again, that really kind of highlights the kind of differences between, what the approach that Dedekind is pushing for, and the kinds of things that you see in Chronicler and the more computational mathematics before that. Yeah, good. So thank you.
So I would say we have the last question by Steve, and then we will close the.
Oh, I get the last word. Okay. What about consistency? It seems to be looming over the whole issue, but we haven't said anything about it. I mean, the idea, you can't just write down any old junk and then expect there to be something that has those properties. And of course, one way to show that there is something that has those properties is to show that there is something that has those properties. But another way is to show that it's somehow, or maybe what you're actually showing is that the properties are somehow formally consistent, or maybe not. Maybe that's just a kind of a extreme cases, and maybe formal consistency is not the real issue. There's something more to it. Is there any, I mean, Hilbert famously finally said, it's just consistency is the same thing as, formal consistency is the same thing as mathematical existence. But in these days and times that we're talking about there, did they have a similar idea of consistency as the touchstone, or as evidence, or as a desideratum? What's the story with consistency?
Yeah, so that's a very good question. So the reason, I studied Dedekind, I mean, the reason I chose this line of research was exactly, I'm a born and bred proof theorist in the Hilbert style tradition. I'm a Hilbert guy, so I'm coming at this from trying to understand sort of the mathematics behind Hilbert's program and the proof theoretic program, and so on. And so the questions you ask are exactly the right ones to ask. I mean, of course, there are the things that, then Hilbert is grappling with, and there's the semantic notions of consistency and the formal notions of consistency and the relationships between them. As far as I can tell, in the 19th century, I mean, there are concerns about, about a meaning and appropriateness and so on. They're not certainly not phrased in terms of having models and so on. I mean, I'd say that, these are the developments that kind of led to the modern way of thinking about consent. I mean, these raised the questions, which then, it became the task of the 20th century to try to resolve and sort through and solve. I mean, you do see, Dedekind trying to construct the natural. He's saying, we know what the natural numbers are, but let's give a construction. So, and it's similarly with the real numbers, right? So you do see him giving a construction to show, to do, right. And the motivation, of course, is he says that, look, I want to make, our talk about analysis, I want to make it rigorous. So I'm going to give you a construction of the real numbers so that we can actually, prove that the square root of 2 times the square root of 3 is the square root of 6. Yeah, I mean, the concerns as to where these sets or systems come from. So yeah, in the 19th century, I don't know of any expression like, well, how do we know that talk about sets is consistent and so on. So as I mentioned, there are times when Dedekind, characterizes them as logical constructions, and so they somehow they're somehow built in. But yes, the questions as to what justifies them, where do they come from? Certainly, they weren't posed in the modern form. And I don't really have a good answer as to how people thought about them in the 19th century, but they're what made the questions salient going into the 20th.
But maybe I know I'm not supposed to have another question, but I don't mean consistency of set theory. I don't mean, is it consistent to give the set theoretic constructions? I mean, the idea that you can specify some new elements by giving the rules to calculate with them. I mean, those rules for calculating. The consistency of those rules is somehow equivalent to the existence of a model which we give in set theory. But so that's what I mean. I don't mean, are the rules of set theory consistent? I mean, are the constraints that we're trying to satisfy in our calculations consistent?
Yeah, so I think if you think about the Chronicarian thing, where you sort of write down some symbols and give to rules to calculate with them, I think they're the thing that convinces you that they're okay, is that you can think of the objects as being the symbol, they're just pairs of numbers, or they're just tuples of data, and there's certainly nothing problematic about them. So I think, you can view it, the Chronicarian approach is that by giving these symbolic representations, you're representing them as, it's like you're saying, well, what are the complex numbers? Well, they're just pairs of real numbers. If you know what the real numbers are, then you know what the complex numbers there. So I think it's trying to, give new calculations of things in terms of old. There's still the question of, well, okay, so if you make up this calculus, how do you know you're not going to be able to simultaneously show that, 2 is less than 5 and 2 is bigger than 5, how it relates to other things. I don't have a good story as to, so I think that's another good question. One could look at again, these more calculational developments and try to think about whether people worried about questions like that and how they did.
Okay, so we will banish Steve for invading the last. Okay, so I think we finished for today. I would like to thank Jeremy for joining us today, and so we have a silent round of applause. So thank you, Jeremy. Thank you very much for your talk. And I would like also to thank all the people that joined us, especially because this was a very long meeting. So for the people that stayed until the end, thank you very much. And I would say we meet in a couple of weeks, and there will be Mike Schulman, and I still don't know the title. I will let you know and inform you. So thank you for joining, and for today, you're free to go.
Thank you, everybody. I enjoyed this very much.
Great talk. Thank you.
Thank you.
Thanks. See you around.
Jeremy left. Okay.